have to use. One is the criterion, and the other one is the expression of the gradient. I can compute G, and I can compute gradient of G, and neither this and neither this needs to do inversion. Doing H transpose, no problem. H multiplied by F, no problem. There is not any inversion to do. So I can compute the value of the criterion that I want to optimize, and I can compute the gradient of the criterion. So I am going to use what is, if you are able to compute a criterion that you want to minimize and the gradient of the criterion that you can compute, what is the natural algorithm that you can use is a gradient-based algorithm. How does it work, a gradient-based algorithm? It's very easy. If I had only one unknown, and if I had a criterion like this to minimize, this is F. I assume that I have only one F, but this is not the case. F is a huge dimensional vector, okay? But just to fix the idea, if I had only one parameter, one pixel, and I wanted to compute G of F, this is the value of G of F, and this is the solution that I want to find. I want to find this point. Okay? How to do? I can start by an initial point. Nowhere. Anywhere. 0. I can start by this point. This is F0. For this value of 0, I can compute the value of G. G of F0. Okay? And I can compute the gradient. Gradient shows this. This is the gradient. This shows the gradient, derivative. And so, if I know that if I am here and the gradient at this point is positive, I have to go at the opposite side. If I have chosen here, I have to go this side. If I am here, I have to go to this side. Optimization algorithm, and we started by telling that because I can compute the value of the criterion and I have the expressions of the gradient, it is natural to use a gradient-based algorithm. If I couldn't compute gradient, there are other techniques, simplex method, for example. But here, because I am able to compute the criterion and the gradient of the criterion, we are going to use the gradient-based algorithms. And the gradient-based algorithm is an iterative algorithm. The word iterative means that you compute the solution in an iterative way. So it means that you do an initialization. Very often we can start by 0, why not? And then at each iteration, k plus 1, we compute the solution. We take the solution in the previous case. We take the solution in the previous case, previous iteration, and add some corrective. And what is the natural choice of the correction? What is the natural choice of the correction is that, imagine this situation that I have shown here. If I have started by F0, which is equal to 0, and if at this point the expression of the gradient of G at point F0 is positive, means that the minimum is at the right. if I have started by this point, here the gradient is this way, so I have to go to the left. At both cases, I have to go in the opposite direction of the gradient. Opposite direction of the gradient. Opposite means minus a coefficient which is called a step function, and we go at the opposite direction of the gradient computed at the previous iteration. So this is just. And if you iterate this a great number of times, here, you were here, you go to right, but how far? This shows how far to go. From here, I go to the right and step this. This will be the next one. Again, I compute here the gradient. The gradient still is positive. I have to go to the right. So the next step is here. The next step is here. And you see that slowly, this is f at iteration 1. And you see that I am going to arrive. And when I arrive here, when I arrive near the solution, this term becomes smaller, and smaller. And at the end, if I see that there is no more change, means that I have arrived at the optimum. Because at each iteration I take the value of previous plus something which is proportional to gradient. Gradient is going to down. Arriving at 0 means that I am not going to change anymore the solution. So I have arrived at the optimum value. So we can iterate this up to the time that the expression of the gradient or the difference between this and this becomes very slow. If the norm of the gradient becomes less than, say, 10 power minus 8, I stop. It is no more necessary to go further. I have the final solution. Okay, so now let's see how much does it cost, because you have to do a lot of time this step. If you choose it a constant value, you can choose it a constant. If you choose it a constant, and if you take a short step, okay, you are here. You have taken a short step. You may take a long number of iterations to arrive at the solution. But it is sure, because if you have taken a very short step, you may stop here, but you are not very far from the optimum. If you take a value of alpha which is large, you go faster, but you may, if you arrive here and then here, you go over. And if you go back, you may come here. And you may oscillate. So alpha, there is a condition on alpha. Alpha, if it is constant, does not depend on the iteration, has to be less than some value. There are some idea how to choose alpha. For example, alpha must be less than or related to the number of the conditions of the matrix or determinant of the matrix. There is some tools to define what is the value of the lambda to obtain. But it is more difficult. But you can also change the value of alpha at each iteration. You can change the value of alpha at each iteration. When you are very far, you can go very fast. And when you are arriving at the optimum, you can go slowly. And so the value of alpha can be adapted to the situation. And one of the way to adapt the value of alpha is look at successive iterations. Look at this point and look at this point. You can compute the gradient at this point and the next gradient. So needs, if you want to adapt this, needs to compute the gradient at previous iteration and at the current iteration. If you have the value of gradient at the previous iteration and the current iteration, you can try to optimize this value of this criterion. And how to do? We want to go as faster as possible, but not too far. Okay? Well, how to do is, okay, if we have a criterion which was any criterion, we can try to say that, okay, from this point and this point, I can define a quadratic function passing by these 2 points, a quadratic function passing by this point and this point, and try to go as fast as possible to go to the optimum of this quadratic function, this approximate quadratic function. If at the origin the criterion is quadratic, it is no more. You can go very fast. But if the criterion at the first is not optimum, is not quadratic, you design a quadratic function which is here, and you can go up to here. And again, you can follow. So let me write how we can do it. You can try to minimize or maximize. Maximize g of f k plus alpha times gradient minus, no, just this. You try to minimize as a function of alpha this expression. So you want to go to the lowest value, because this is the next operation. You are going to find, well, this is called steepest descent technique, which is called steepest descent. You are going down, but with the steepest descent to go to the valley. Okay. So let's put these details, which are more. You have many books on the optimization. There are many other methods. I have just written here the simplest method of optimization. There are conjugate gradients and Newton methods, the second order methods. Gradient-based methods are called first order methods. You have zero order methods, which are when you can compute only the criterion. And you have the Newton methods, but Newton methods will not be applicable in this case because it needs to compute the Hessian matrix, so it is more complicated. So we are going to stop to this gradient-based method. But let me go a little further in the details and to see how much does it cost. Okay? Because the main point was that H is huge dimensional and we want to compute this, and H here is huge dimensional. We have to compare if we use this method or if we use this method, which one is better. Okay? And I pretend that this method is more applicable than computing directly the solution. Let's show it. Let's go a little more in details of. For now, I am not going to talk about the value of alpha. Let's see if the value of alpha is fixed or what will be the cost of the computation. So here I have what is the expression of this gradient here. So we will have the expression of this gradient is here. I can put -2 in factor. So -2 in factor, minus and minus becomes plus. So I have this algorithm. F at iteration k plus 1 is f at iteration k plus alpha gradient. And gradient is H transpose G minus HF, F at iteration K, and what else? Minus lambda F at iteration K. This is what I have to do many times, okay? Let's see what are the costs of the computation. This term, no, so this is not so important, the computation to do. The steps are here. How to do this? Let's call this G hat. G hat at iteration K. Let's call this delta G at iteration K. And let's call this delta F at iteration K. Actually, there are this part plus this. This term does not cost too much, so I am not talking about. Or imagine that lambda is equal to 0, just to see that the main part of the computation is these 3 steps. This step, regularization part, in general, is not too much costly. So let's see, to compute this, G hat equal to HF. HF hat at iteration K. How much does it cost? You have a matrix multiplied by a vector. So how much operation? The matrix is n by n, vector is n. So you have n2, n power 2 operation. Then you have to compute delta G, which is G minus G hat. This doesn't cost too much, say 0, subtraction. And then you have to compute delta F, which is H transpose delta G. H transpose, you remember, is adjoint operator. You have the matrix, you have to transpose, this doesn't cost. And if the matrix is n by n, doesn't change, n2 operation. So you have 2 n2 operation per iteration. Okay? If you need to do, say, 100 iteration, in practical applications, 100, 200 iterations are enough. So if n is, if in one-dimensional case, even in one-dimensional case, it is better to do that. You see that very fast. This method is more useful than computing directly the inverse. Okay? And one of the main advantage, more than the computational cost, is that you do not need to construct the matrix H and to do the multiplication. Actually, what you need is, you do not need H by itself multiplied by F. What you need is the result. And this operation, which is here, is what? Computing the forward problem. This is computing the forward problem. And the forward problem, for example, in the case of convolution, we saw that the forward problem was a convolution to do. And a convolution can be done very fast. And you do not need to construct the matrix by itself. You need just to know the impulse response. You give the impulse response and F, and you compute the solution. Do you see this? And how about this? This is apply the adjoint operator. Forward operator, adjoint operator. Adjoint operator, if the matrix was in convolution, if the matrix was toplets, changing the dimensions, still it stays toplets. So it means that again this would be a convolution. There is not inversion of the matrix. So you need actually two programs, two MATLAB programs. One may be called direct adjoint or forward adjoint. If you have these two programs, then you can write very easily, just in one line, your algorithm here. And this technique would be applicable in all the inverse problems. Do you see the point or not? So how the optimization algorithms is going to work? No, there are much more to know about the optimization algorithms. For example, here in place of let me finish with that and then coming back to this point. So you see how it works. Actually, if you write, let me again insist on this. In the first step, which is here, second step, which is here, third step, which is here. And also this scheme shows you how the algorithm works actually. How it works. You have a solution. You compute the output of the model. So you have a f0, fk, f at iteration k is given. You compute g hat. You had the data. The data is g coming here. You make the difference. This is the residual error, delta g. And what you are going to do is you take this delta g and you are back project it in tomography. That will be projection and back projection. Forward operator, adjoint operator. So you do H transpose, and here you take the solution and you add it. So let me show here how to add. Here it is. And this algorithm continues, and somewhere you will stop here when and this is the output of the algorithm. Do you see how this works? That's an iterative algorithm. At each time you have a solution. You come here to add some addition. You obtain a new solution. This new solution gives you G. You compute the difference. You come here and you compute U. The word for that is forward model, adjoint operator, and here we have the residual. You have the data. The data comes here. The residual. If the residual becomes 0, if this becomes 0, if that term was not exist, if this term becomes 0, okay, you will stop. But actually, in fact, this is the prior information who comes actually where? This prior information comes here. You add some, say, another delta f coming from the prior information, which will be added somewhere here. From this, you have